So up until this point, we have looked at ions and the way they bond to form ionic compounds. But today we're going to take a look at metallic bonds, and this occurs in any of the metals that are on the left of that stair-step line. So metallic bonds will occur in crystalline solids, and in these metallic bonds, every point on the crystal structure is going to be occupied by an identical atom. And this is different from what we've been talking about with the ions, because those had the alternating positive, negative, where here we just have the total neutral atom side by side. Different things with the metallic bonds is that the electrons, specifically the valence electrons, are mobile. That means they move and they're not in a fixed location around a nucleus. They have the ability to drift from one atom to another, and we call these free range electrons, and we call them delocalized, meaning that they do not have a specific home anymore. So a metallic bond is the attraction of the stationary metal cations, which are these bigger brown circles, and they are attracted to these mobile electrons that have this free-floating capability. And remember, it's just the valence electrons that are free-range electrons. So other properties of metals, we probably know this already, but metals can conduct heat and electricity very well. And this is due to their free-range electrons that are moving. Metals have that luster or that ability to look shiny. And this is due to their valence electrons getting excited and absorbing energy when light hits it. And when electrons get excited, they move to higher orbitals or higher energy states, and move to higher energy states. And almost immediately, as soon as it reaches that higher energy state, it will fall back to the ground state. And when it does that falling, it emits light. And that light is that luster that we see. So to kind of go back through that, the luster is due to electrons getting excited as the light hits it. They move very easily to the higher energy states because they're free-flowing electrons. As soon as they absorb that energy, they go to the higher energy states, and then they fall right back down to the ground state. And when they do that, they emit light. Another characteristic of metals is malleability and ductile. Malleable is the ability to be hammered into sheets, like aluminum foil or tin foil, and ductile is the ability to be stretched into wires, such as copper wire. This is able to happen because the free-flowing electrons will fill the spaces between the cations when a force is applied to a metal. So instead of shattering like the ionic compounds because of the similar charges repelling one another, the free-flowing electrons will fill the spaces between the cations to prevent this shattering from happening, so they kind of become more flexible, so to speak. When we look at the crystal structure of metals, they exhibit a phenomenon called closest packing, and this is the most efficient way to pack spherical objects. in a more geometric pattern. The spherical objects here are going to be the atoms. And so there are three specific structures that you can get. You can get cubic bodied centered. We abbreviate that one BCC. Iron, vanadium, niobium, and chromium use or display cubic body centered. In these, we have atoms at 8 corners, and then 1 located in the center. And then the coordination number for each of the atoms is going to be 8 in this particular closet packing or closest packing structure, sorry. Our second structure is going to be cubic face centered, or FCC. So it's basically the same as cubic bodied, but instead of there being an atom in the center, there's going to be an atom in the middle of each of the faces. So we have the 8 corners taken care of or occupied by atoms, and then 1 in the center of each face. And so that gives us a total of 6 atoms there. The coordination number for any of the atoms found in a cubic face centered structure is going to be 12. And then hexagonal, this is pretty much the same as the cubic face center in that the coordination number is going to be 12. But this time, instead of forming a cube, we're going to have a hexagon shape. So again, here are the elements that do the hexagonal: titanium, zinc, magnesium, and cadmium. Lastly, metals have the ability to form alloys. Alloys are mixtures. They are not compounds. And the distinction here is a mixture is not chemically bound. The atoms are not chemically sharing or transferring electrons. So an alloy is a mixture composed of 2 or more elements, and one of those elements must be a metal. So a couple or 3 pretty common alloys are brass, bronze, and steel. Brass is made up of copper and zinc, bronze is copper and tin, and there are different types of steel. The main element in steel is iron, and then you can have any one of these other atoms be found in steel. There are 2 types of alloys, or kind of subcategories, the substitutional alloys and the interstitial alloys. Substitutional alloys have atoms that will replace each other in the crystal lattice, and then interstitial alloy atoms are where smaller atoms such as carbon will fit between the larger metal atoms. So interstitial kind of is in between. And so with that, I'm not too worried that you know the specifics of the substitutional and the interstitial. I'm more worried that you know what an alloy is, and then these 3 examples. So the homework for tonight is the lesson review questions 1 through 8. Again, if you have any questions, feel free to contact me through Remind, and I will help you as best I can.